Okay, so continuing in section 11.2, talking about polygons, um, we just identified simple, closed, convex, concave, um, polygons, and so on. And so here in this next slide, I need us to understand, kind of relating this back to some of the early geometry stuff that we've talked about in section 11.1, as far as points and lines and planes. You need to understand that if a polygon is in a plane, so again, think about a plane as being a flat surface that continues forever in all directions. Um, so maybe the table that you're sitting at, or the floor, or the ceiling, or a wall, any of those things could be considered um, to be planes. And so if a polygon is sitting in a plane, like in this example that you see here, you can see all of this exterior part represents the plane, that square type shape. And then if there's a polygon sitting in that plane, it forms three distinct parts. There's the exterior of that, which is all the stuff that's out here. All of this stuff is considered the exterior in that plane. Then you have the interior, the stuff that's on the inside of that polygon. And then you have the actual polygon itself. And so there are three parts here. We may talk about things that are inside. We're going to talk about some angles later that are inside the polygon. We may talk about angles that are outside the polygon, or other things that are outside the polygon. And then we're going to talk about the polygon itself. And so when a polygon is sitting in a plane, it has three distinct parts: exterior, interior, and then the curve itself, or the polygon itself. Now, if we are talking about polygons, which in this case we are, every polygon is going to have at least three vertices. So each of these points where two of our sides meet are considered to be a vertex. So multiple vertices, plural for vertex there. Um, every polygon is going to have vertices and it's going to have sides. So a triangle, for example, has three vertices with three sides. We're going to talk about some others here in the next slide. So we identify polygons based on the number of vertices or number of sides they have. The number of vertices and the number of sides is always going to be the same. And so we are very, very familiar with some of these. Some of these you may not be very familiar with. For example, a triangle. We all know what a triangle looks like. We know that a triangle has this general shape. It has three sides. It has three vertices. Again, that's one that you've seen a lot. We're going to talk a good bit about triangles throughout the rest of this chapter. The next one is what we call a quadrilateral. Now, quadrilateral could be a square, it could be a rectangle, it could also just be some random shape that has, oh, not that, that has four sides. So we could do something like that. It's not very good. I'm not a very good artist. But you could have something like that that is just a four-sided figure. And so that would be considered a quadrilateral. Again, there's a lot of different types of quadrilaterals. We'll talk about specifics here in a little while. The next term is a pentagon. If you are not familiar with what a pentagon looks like, I would encourage you to go Google the United States Pentagon, where the Department of Defense is housed. When you look at it, it is a five-sided building. And again, I'm not the best artist in the world, but it's going to look something kind of like this, where it is a five-sided figure. And again, you could have a lot of different pentagons. That's just one that's common. A hexagon is a polygon that's got six sides. Again, six vertices. Heptagon has 7. Heptagon is one we don't use a whole lot. That is not one that's all that common, but it is one that we need to make sure we know. An octagon has 8 sides. It's going to be your stop sign shape. A lot of times when we talk about polynomials that are bigger than, let's say, 5 sides, usually 6 and 8 are pretty common. You may have, especially in design type things, you may have a hexagon shape, or you may have an octagon shape. We have a patio table that is a hexagon shape. It'd kind of look odd if it had 7 sides. So it usually either has 6 or has 8. And so octagon's pretty common. A nonagon has 9 sides. That's one that's not super common either. And then a decagon has 10 sides. A hendecagon has 11 sides. This is also one that we don't see very often. This is very, very uncommon that we would deal with a hendecagon. But again, it is one that has a specific name. And then if it has 12 sides, it's what we call a dodecagon. After 12 sides, if the polynomial has 13, 14, 15, 20, pick your favorite number after that, we call it an n-gon. So for example, if it has 15 sides, we would say it's a 15-gon. Okay, there's no special name for it after the 12. And so you're going to see problems potentially. I know there's one, I think, on your math lab that says something about a 14-gon. Well, it's a polygon that's got 14 sides. And so just be aware of that. Again, primarily terminology things that we're talking about here. So when we talk about polygons, there are some things that we need to be aware of. First is what we call an interior angle. We talked about interior a few minutes ago. An interior angle is an angle that's on the inside of the polygon. For example, if we were to look at a triangle, an interior angle would be one of the angles on the inside. Depending on how many sides there are, maybe depends on how many, or determines how many interior angles there are. So you could have 3 or 4 or 5 or a large number there. You could also have some other line segments that are in the polygon forming other interior angles. So you could have more than just the number of sides. So just be aware of that. The next term is what we call an exterior angle of a convex polygon. So let's again take a triangle shape here. If we were to talk about an exterior angle, it is formed by one of the sides, so here would be our side, and the extension of another side. And so the exterior angle is this one. It's outside of our polygon. And again, we could do it with triangles or other shapes as well. That is what we call an exterior angle. And then our next one is a diagonal. And so you probably know kind of in your mind what a diagonal is. But a diagonal is a line segment connecting any points of the polygon that are not consecutive. So for example, if I were to give you a pentagon shape, okay, there's 5 sides. If I were to connect this point and this point, those 2 points are considered to be, or the line segment connecting those is considered to be a diagonal. But you could also have a diagonal from those 2 points. But then you can have a diagonal from this point to that point. And you can have a diagonal from this point to that point. And then you even have a diagonal from those 2 points. So you can have multiple diagonals. And so it's any segments connecting non-consecutive vertices. Okay, those are going to be inside our polynomial. Because again, we're primarily going to be talking about a convex polynomial when we talk about diagonals. If there happens to be any questions, feel free to let me know. Shoot me an email or something, and I can clear up any questions that you might have. So in this diagram, you kind of see some of those things we're talking about. You can see, first of all, the interior angle here at the bottom of this quadrilateral. This angle would be an interior angle, or what we may call angle 1 of polynomial ABCD. You also see the diagonal here between points A and C. So again, non-consecutive vertices and the segment connecting those. And then in this other diagram, you can see angle 2, which is an exterior angle. And so as we work with angles and find angle measurements and some of those things, we're going to be dealing with interior angles and exterior angles, and there's going to be a lot of angle measurements that we'll find. And so understanding what's interior versus what's exterior will be important. All right, so let's talk about congruency a little bit. So we say that two parts are congruent if they are the same size and the same shape. Now, we do not say they are equal. Equal implies they are the exact same figure. They may look the same, but unless it is literally the same angle, same segment, whatever it is we're talking about, then we call it congruent. It just means they look the same, they have the same shape, same size, but they're not the same angle, same segment, whatever. Okay? And so we would say that two line segments are congruent, and we use this symbol to represent congruency. It is an equal sign with a little squiggly line above it. And we say that two segments are congruent if tracing one line segment can be fitted exactly on top of the other. In other words, if I were to take two line segments and I could pick one of them up and put it on top of the other one, it would fit perfectly. It'd be the exact same size, exact same shape, everything about it would be the exact same. And I'll show you an example of that in just a second. And we would say that two angles are congruent, again using the same symbol, if they have the same angle measurement. So one 90-degree angle is not the same, not equal to another 90-degree angle. They're congruent because they have the same measure. And so you can see that example here. With our line segments, we would say that line segment AB, so AB there, is congruent to line segment CD. Meaning that if you were to take this segment and pick it up off the screen and lay it on top of segment CD, they should lie on each other perfectly. Now, when we talk about congruency, especially with side length, we oftentimes will use a little tick mark to show that. We will just put a little mark to say these two sides are the same length. If there happen to be more than one set of sides that are the same length, we may use two little tick marks. So we may put two marks to show they're the same. So when you see that, that indicates these are the same length. Okay, so that'll be important to us in a little while. And then if we're talking about congruent angles, in this case, angle XYZ, or ZYX, however you want to say that, has a measurement of 108 degrees. Well, angle PQR, or RQP, again, whichever way you want to say that, it also has an angle measurement of 108 degrees. And so we say they are congruent. They have the same measurement. Again, they are not equal unless they are the same angle. Okay, so we may say, well, angle XYZ is equal to angle ZYX because it's the same angle. Naming it XYZ versus ZYX. Okay, same angle, we could say that those two angles are equal because they're the same, but typically we talk about congruency, what has the same angle measurement. And so one of the last things for this video that I want us to talk about is what we call regular polygons. So regular polygons are polygons whose sides and angles both are congruent. All sides and all angles being congruent. So, in the two examples that you see here, in this pentagon, it is what we call a regular pentagon because every side length of this is the same. You see that notated with little tick marks. And then also every angle measurement is the same. By the way, if your angle measurements were not the same, we may use one little mark for one angle, then we may use two little marks for another angle, or three marks, depending on how many angles there are. And so in this case, every one of those angles in that pentagon are the same measurement. So they are equiangular and also equilateral. In the second example, you see a regular hexagon. So it's got 6 sides, and it too is equilateral because all the sides are the same, and it's also equiangular. And so again, that's going to be really important. So let me ask you this. Is it possible for a polygon to be equilateral and not equiangular? So think about that for a second. And then also I want us to think about, is it possible to be equiangular and not equilateral? Okay, so that's what's coming up next. So I want us to think about that. I want us to try to come up with an example of a polygon that is equiangular but not equilateral, and draw a sketch. And then also I want us to try to sketch a polygon that is equilateral but not equiangular. So what I encourage you to do is pause the video for just a second, think about this, try to come up with an example, and then I'm going to give you one here in just a second. So if you need to pause the video, do that. 3, 2, 1. All right, so let me give you an example. So when we think about equiangular but not equilateral, the first thing that comes to my mind is a rectangle. If we were to take a rectangle, we know what a rectangle looks like. In a rectangle, each angle is 90 degrees. It is equiangular, but it is not necessarily equilateral. So in this case, these two sides are congruent, and then also the top and bottom sides are congruent, but they're not all congruent. So it's not equilateral, it's just equiangular. So that's one of several examples you might come up with. And then for part B, a polygon that is equilateral but not equiangular, well, what I think about, again, this is just kind of first thing that comes to my mind, is a rhombus shape. So we're going to talk about a rhombus in a few minutes. A rhombus has the same side lengths, but it is not the same angle. So every one of these sides would be the same length. But obviously you can see that this angle measurement and this one at the top are not the same. And so because of that, we'd say, oh, well, that shape is equilateral, but not equiangular. Again, if you have any questions about that, please email me. This would be the point in class when I would ask if there are questions, and I would wait for you to give me a response. So if you have a question, please let me know, and I'll try to answer that. I'll continue this chapter with another video in just a minute.